In this video, we're going to start learning processes for solving differential equations. And what we're going to do is proceed with various types of equations. So these things, we're going to be looking at linear differential equations with constant coefficients. Homogeneous ones at first. So these look like this, like a sub n y, the nth derivative of y, plus a sub n minus 1, the n minus 1th derivative of y, plus dot 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 plus a sub 1 y prime plus a sub 0 y, and that equals 0, where the a sub I are real numbers. And the process probably was inspired by the following equation. So let's take a look at this thing. Solve. Say we have a y prime plus by equals 0. There's a number of ways you can do this, integrating factor, or you can separate. I probably will go with separation. I think I'll go with an integrating factor here. A and b are real numbers, so I'll use e. Before you do any kind of an integrating factor, you need to divide first by a, and we're left with y prime plus b over a y equals 0. Now I'll go to the integrating factor, which is the integral of b over a dx, which is e to the bx over a. And of course you multiply everything by that. So we have e to the bx over a y prime plus e to the bx over a times b over a y equals 0. Of course, the left side becomes the differential of e to the bx over a times y. That's equal to 0. And that means that e to the bx over a times y is a constant. And then, of course, then we get y equals a constant times e to the negative bx over a. Well, what someone noticed was that these kinds of solutions pop up a lot when you have constant coefficients. In fact, if you were to take and check that, just the negative e to the negative bx over a part, when you go and do the derivatives, plug that in, we're going to get negative b over a e to the negative bx over a plus b over a e to the negative bx over a. Of course, it does equal 0 because these two completely wipe each other out. Someone somewhere decided to look at equations of this form. Let's say we have y double prime plus, and now we're doing constant coefficients, so I might want to do a y prime plus by. This one would have already been, the leading coefficient would have already been divided out. And they suggested trying y equals e to the mx. Here m could be any kind of a number that works. Well, let's go ahead and throw it into the equation. So we'll have e to the mx double prime plus a e to the mx prime plus b e to the mx equals 0. I was a little bit too quick on this middle piece here. The derivative is not ay, but just the y part. And the idea is we'd figure out m later. Like if I plugged it in the first equation and I got something, I would be able to find out that m equaled negative b over a, for example. I'll show you how we do that. Let me go ahead and take the second derivative here. The first derivative is m e to the mx. The second derivative will be m squared e to the mx. The second one then one that's just first derivative, will be a m e to the mx. And then finally we have plus b e to the mx. Set that equal to 0. I can factor out e to the mx from everything, leaving me with m squared plus am plus b equals 0. Now here's the tricky part. E to the mx, this part right here, does not equal 0 no matter what m is. Or for any values of x, this never equals 0, so I can divide by it. That leaves me with the following equation. Well, here, if these were x's, you had seen it before. This is just a quadratic equation. We can solve something like that with the quadratic formula, or if we luck out, we can use factoring. So the e to the mx disappears from the problem. As far as this is concerned, it strictly becomes an algebraic problem now. Let's do an example to illustrate this. Let's solve y double prime plus 4y prime plus 3y equals 0. And we're going to let y equal e to the mx in the hopes of finding out what m is equal to. So let's plug it in. So when we plug it into the equation, we'll get m squared e to the mx plus 4m e to the mx plus 3 e to the mx. That, of course, is supposed to be equal to 0. So let's go ahead and factor out the e to the mx. We're left with m squared plus 4m plus 3 equals 0. Notice how similar the m squared plus 4m plus 3 looks to the original equation. In fact, if I had replaced these y things with m's, that would be exactly the same expression. Divide by e to the mx as before. And we're left with m squared plus 4m plus 3 equals 0. Not only is this a quadratic equation, but I can factor it. M plus 1 times m plus 4 equals 0 plus 3. And so m equals negative 1, negative 3. That means my general solution looks like the following. Y equals c1 e to the negative 1x plus c2 e to the negative 3x. Of course, we already know they're linearly independent because e to different powers of x like that will automatically yield a non-zero Wronskian. Now, you might want to try either one of these things in there to make sure that it works. Example 2. Solve y double prime minus 10y prime plus 25y equals 0. We play the same exact game. Here we're going to do y equals e to the mx and then figure out what m is. Throw it into the equation. We'll get m squared e to the mx minus 10m e to the mx plus 25 e to the mx. That equals 0. Once again, divide by e to the mx. Once again, look how similar this equation looks to the original differential equation. In fact, many of the times, we'll do this kind of substitution or set y equal to that, and we will just automatically jump right to this equation. This equation has a name. It's referred to as the auxiliary equation. And that's the thing that we're going to try to solve. Here, we have m minus 5 times m minus 5 equals 0. And so we get m equals, now this is a repeated 0, so we have m equals 5 and 5. Now remember, these things usually have two linearly independent solutions. So if you try to do this for your answer, The problem with these two is they're not linearly independent. One is equal to the other one, so this does not give two linearly independent solutions. So we already know that one solution will be e to the 5x, but we can't necessarily have this. So we now know that y1 equals e to the 5x is a solution. So the same thing that we did in the last section, we're going to use that to find another solution. So with that in mind, set y equal to u y1, which is of course u e to the 5x, and let me take the series of derivatives with the intent of plugging it into the equation and figuring out what the other, or y2, is equal to. So y prime equals u prime e to the 5x plus 5u e to the 5x. Y double prime equals u double prime e to the 5x plus 10u prime e to the 5x plus 25u e to the 5x. And we're going to plug all those things into the equation. Now, one thing I'm going to do is I'm going to factor out the e to the 5x practically as soon as I get in there. Our original equation was this. All right, so in my y double prime, I'm going to have e to the 5x times u double prime plus 10u prime plus 25u minus 10. I'll pull out the e to the 5x there as well. And we'll have u prime plus 5u. And then finally, plus 25 e to the 5x times u. Set that equal to 0. Divide everything by e to the 5x, and we end up with u double prime plus 10u prime plus 25u minus 10u prime minus 50u plus 25u equals 0. And I noticed that the u's are supposed to cancel, and they absolutely do. But we lucked out here in that u prime also canceled. And we end up with just u double prime equals 0. Well, hopefully you know that if a derivative is equal to 0, then the function itself was a constant. And then once I know that, I'll know that u is cx. So we can use just u equal to x. So when I'm creating my y2, u y1 will equal x e to the 5x. And so our solution is actually y equals c1 e to the 5x plus c2x e to the 5x. And that's how multiple or repeated zeros works. If we have multiple zeros, what we do is we end up throwing an x onto the solution, and this will give us a linearly independent one. Suppose y equals e to the mx is a repeated solution to a sub n y to the nth, or the nth derivative of y, a sub n minus 1, y n minus 1, a1y prime plus a0y equals 0. Suppose e to the mx is a repeated solution. That means we have e to the mx is repeated, say, k times. That means when you solve the auxiliary equation, that means when you solve a n m to the n plus a n minus 1 m to the n minus 1, when you solve that, so suppose this is repeated k times. Say when I solve this, I get m equals m naught, m naught, m naught, m naught. Suppose I get these k times. Then part of your general solution will look like this. So what you'll get is you will get c1 e to the m sub 0 of x, but then you'll get c2 x e to the m sub 0 of x. Then you'll get c3 x squared e to the m 0 x. And this will go on and on and on until you finally get, if it's repeated k times, then you're going to get to a ck. And then you're going to have x to the k minus 1 e to the m sub 0 of x. So you just keep incrementing the power on x to give you linearly independent solutions. So as an example, if I have the equation y double prime plus 4y prime plus 4y equals 0, I can immediately go to the auxiliary equation, and this thing factors as m plus 2 times m plus 2 equals 0. And so m equals negative 2, negative 2. Therefore, my general solution is c1 e to the negative 2x plus c2x e to the negative 2x. So that takes care of the repeated zeros case. Then we have some other cases that I need to discuss, some things that will pop up that may surprise you unless I've talked about them first. Let's look at something like this. Here we have 3y double prime plus y equals 0, so we go to 3m plus 1 equals 0. There's our auxiliary equation. 3m squared plus 1 equals 0. Then m squared equals negative 1/3, so that m equals plus and minus the square root of negative 1/3. Well, this here equals plus and minus 1 over the square root of 3, but times I. It's an imaginary number. That happens sometimes when you solve equations of this type. So what we have then is our solutions. One way to write the solutions is this. Y equals c1 e to the x over radical 3 plus c2 e to the negative x I over radical 3. I forgot my I on the first one. Let me get that in there. Now, if we're going to only deal with real numbers in here, certainly don't want to deal with the imaginary exponents. So we have a way of dealing with something like this. And it's from something that you may or may not have seen before, but recall. This is actually something you saw in trigonometry. Probably getting close to when you were looking at roots of unity and things like that. There is an equation that goes like that. E to the I times theta equals cosine of theta plus I sine of theta. So, let's take a look at our answers. We have e to the 1 over radical 3 times I. I can use, my theta here is the 1 over radical 3, so I'll have cosine, and I probably should put my x in here. I forgot my x, so I'll put my x in there. It's cosine of x over radical 3 plus I sine of x over radical 3. And then the other solution was e to the negative 1 over 3 radical 3x times I. That equals cosine of negative radical 1 over radical 3x plus I times sine of negative x over radical 3. Now cosine is an even function and sine is an odd function. So cosine can squash its negative, but the sine I'll have to pull it out front. Now, if I add this equation, if I add the e to the 1 over radical 3ix to the other solution, I will get 1 times e to the 1 over radical 3x times I plus 1 times e to the negative 1 over radical 3xi. And according to what I have here, when I add them together, the sine terms cancel out, and I'll get 2 cosine of x over radical 3. What that means is, since 2 cosine of x over radical 3 is a linear combination of these two solutions, it too is a solution. Now, if I subtract the two things, and say I do 1 times e to the 1 over radical 3xi minus 1 times e to the negative 1 over radical 3xi, this time when I subtract them, the cosine will go away and I'll get 2i sine of x over radical 3. So both of these things are solutions, and if you do the Wronskian on cosine versus sine, you're guaranteed to get a non-zero answer. What I mean is these will be two linearly independent solutions as well. So instead of writing our general solution as C1 e to the 1 over radical 3xi plus C2 e to the negative 1 over radical 3xi, I use the fact that here's two linearly independent solutions. I'm going to use y1 will be my cosine version, y2 will be the sine of x over radical 3, and I can instead use y equals C1 cosine of x over radical 3 plus C2 sine x over radical 3. So immediately, whenever you see non-real zeros, you know that you can break it down into here. And right here now, if we stick to real constants here, if we want, we can stick to real constants here. I never have to worry about having an imaginary solution that way. Next example, let's do that one. Another one real quick like it. Y double prime plus 25y equals 0 converts to m squared plus 25 equals 0, or m equals plus and minus 5i. I can immediately go to y equals C1 cosine of 5x plus C2 sine of 5x. That's almost all the stuff with imaginaries, but we can have more complicated non-real solutions than just something attached to an I. And that's what the next example is going to show. We have 2y double prime plus 2y prime plus y equals 0. So the auxiliary equation is 2m squared plus 2m plus 1 equals 0. Now this doesn't factor, it doesn't look good, so I'm going to go to the quadratic formula. And if you recall, that's negative b plus and minus b squared minus 4 times a times c all over 2 times a. And let me do a little simplifying. Negative 2 plus and minus. I'll have inside, I'll have 4 minus 8, so I'll have negative 4 in the square root. And that, of course, is negative 2 plus and minus 2i over, I made a mistake in the denominator, that's 4. Or perhaps a little simpler is negative 1/2 plus and minus I over 2. So those are our two solutions. And this would give us all of our answers except what happens next. Notice that this is not just I over 2. Otherwise, I would be able to work this. However, if I do e to the negative 1/2 plus and minus I over 2 times x, I'll get e to the negative 1/2 x plus and minus 1/2 x times I. I just did a little rearranging up top there. And then I can rewrite this as e to the negative 1/2 x times e to the plus or minus 1/2 xi. And then this part right here, this stuff right here, the e to the negative 1/2 x is something that'll just factor out of everything. This part here we can replace with our C1 cosine of x over 2 plus C2 sine of x over 2. So these are no big deal. You'll just factor out what's called the real part of this particular answer here and strip it out and put it out front. For our next example, we have 2y double prime minus 3y prime plus 4y equals 0. And it will immediately go to 2m squared minus 3m plus 4 equals 0. It may factor or it may not. I really don't care. I know this formula well enough that I'm not going to bother with trying. So we have negative b plus and minus. B squared is 9 minus 4 times a, which is 2, times 4, which is c, all over 2 times 2. So we have 3 plus and minus. Let's see what's inside of here. 4 times 4 is 16, times 2 is 32. 9 minus 32, so we have negative 21 inside of there, all over 4. So we have 3/4 plus and minus. It's important for you to strip out the real part from the imaginary part in order to apply the answer. Plus and minus radical 21 over 4i. So therefore we can write our answer as y equals e to the 3x over 4 times c1 cosine of radical 21 over 4x plus c2 sine of radical 21 over 4x. Now let me do one example with some initial values. So suppose we have 4y double prime minus 4y prime minus 3y equals 0, but we have y of 0 equals 1 and y prime of 0 equals 5. All right, so going to the auxiliary equation, we have 4m squared minus 4m minus 3 equals 0. M equals 4 plus and minus 16 minus 4 times a, which is 4. C, though, is negative 3. So my answer is going to be real. All of that is over 2 times a, which is 8. So we get 4 plus and minus. Let's see what we get inside of here. I have, oh, this is nice. 16 plus 48 is 64. All over 8. So we get 1/2 plus and minus 1, which will be 3/2 and a negative 1/2. So we know that our solution is y equals c1 e to the 3x over 2 plus c2 e to the negative x over 2. Now I'll need to figure out these numbers up here. So y of 0 equals 1. tells us that 1 equals c1 e to the 0 plus c2 e to the 0. And there's one equation. I'll need a second equation to solve for c1 and c2. I know that y prime of 0 equals 5. And so I'm going to have to take my solution and take its derivative. So y prime will equal 5 c1 e to the, not 5, 3 halves c1 e to the 3x over 2 minus 1 half c2 e to the negative x over 2. And so when I plug in 0 to get 5, I'll have 5 equals 3 halves c1 minus 1 half c2. What I'm going to do just to make this equation a little more palatable is I'm going to multiply it by 2 to give me 10 equals 3c1 minus c2. So my pair of equations look like this. c1 plus c2 equals 1, and 3c1 minus c2 equals 10. So obviously add them together to get 4c1 equals 11, or c1 equals 11 fourths. And then I'll write the equations again. This time I'm going to wipe out the c1. So I'm going to multiply the first equation by negative 3. And then when I ultimately add them together, the c1s will cancel out. But then I'll get negative 4c2 equals negative 3 plus 10 will be 7. So c2 will equal negative 7 fourths. So my solution then is y equals 11 fourths e to the 3x over 2 minus 7 fourths e to the negative x over 2. Now this takes care of all of the possibilities that could happen when you have a quadratic auxiliary equation. What happens when we have higher order equations? This goes still to the auxiliary equation, so m cubed minus 1 equals 0. Now if you try to solve this, there's only one real answer, and that's 1. So you won't get all three solutions based on just adding 1 to both sides and then taking the cubed root. However, if I factor, I get the following two factors. So of course m equals 1 is a solution, but the other solution is contained inside of this quadratic. So when I set m squared plus m plus 1 to equal 0, I'll get m equals, and I'll use the quadratic formula, negative 1 plus and minus 1 squared minus 4 times a times c, all over 2 times a. That's negative 1 plus and minus the square root of negative 3 over 2, or negative 1 half plus and minus radical 3 over 2i. And so then our solution is going to be y equals c1. My first solution had a 1, so I'll have e to the x plus c2 e to the negative, well actually probably it's best to do, there's two solutions. Remember this part here is going to give us a cosine and sine, and they'll have c1 and, or c2 and c3 attached to them. So let me take the c2 out of here, and we'll do e to the negative 1 half x times c2 cosine of radical 3 over 2x plus c3 sine of radical 3 over 2x. And there is our complete solution. Next one is the fourth derivative of y, minus 2y double prime plus y equals 0. So we go to m to the fourth minus 2m squared plus 1 equals 0. This factors to m squared minus 1 squared. Or I'll set m squared minus 1 equals 0. So m equals plus and minus 1. Well, what we have here, since it was squared, I actually have the following solutions. I have plus or minus 1 are each repeated. So you'll get y equals c1 e to the x plus c2 x e to the x. That takes care of my repeated ones. Plus c3 e to the negative x plus c4 x e to the negative x. For our last example, we have y triple prime plus 2y double prime minus 5y prime minus 6y equals 0. And so we'll go to the auxiliary equation, m cubed plus 2m squared minus 5m minus 6 equals 0. Now this is a little more complicated because, for one thing, I don't know how to factor this right off the bat. Even if I tried grouping, say I tried to take an m squared out of the first two, I do not have anything out of the second two that I can work with. So what I'm going to do here, there's a number of ways to work problems like this, but I think the easiest thing to start off with is to go to your calculator and see if it comes up with the zeros for you. So that is what I will do. All right, most of you, I assume, have a calculator like this. Let me go into the y equals and clear this, and I'll put this equation in, except you have to use x instead of m. So we'll do x cubed. On these calculators, when you hit the this caret key, it takes you up a notch. You have to use the arrow key to bring you back down to the same level as the x. So we'll have plus 2x squared minus 5x minus 6. Now what I always do is I always do zoom and then 6. It sets a standard viewing screen. So what I see here, if I look carefully, it's hard to see here, so let me go ahead. What I've done is I reproduced the graph onto here, and I can see, at least it looks like through here, that it crosses at -3, at -1, and at 2. So these look like my three values, although I don't trust it unless I actually zoom in and do a bunch of stuff. But let's just see if 2 actually is a solution to that. So if you'll remember, to figure out how, here's what I can do. Not only will I determine if 2 is a solution, but if it is, I will determine on how to factor this the rest of the way. I'll show you what I mean. Perhaps you've seen this before. I can use synthetic division. It will not only tell me if 2 is a 0, because if a 0 appears in this last column, then I'll know that 2 is a solution, but what it'll give me left will be the coefficients of the other factor. The first factor, if this works, will be m minus 2, and the rest of the factors will be revealed underneath of the line. So the first thing you do is you drop your 1 down, and I did that. Then I take my 1 and multiply it by 2 and put it underneath of the next coefficient. Add those together, and then I take 4 times 2. I'll get 8. Add them together to get 3. Then 3 times 2 will give me 6, and lo and behold, it is a 0. So not only do I know that m minus 2 is a factor now, I know that the rest of it factors is m squared plus 4m plus 3. Well, I can actually factor the rest of that stuff. M minus 2 times m squared plus 4m plus 3 equals 0. M minus 2 times m plus 1 times m plus 3 equals 0. So actually we find out now that it did actually cross through -1 and -3. So my general solution then is y equals c1 e to the 2x plus c2 e to the -x plus c3 e to the -3x.